Hi guys, my name is Terry. In this video, I'm going to go through with you additional mathematics form 4 textbook question for chapter 1 function mastery practice. If you enjoyed this video, can you like, subscribe, or leave us a comment if you have any question. Okay, so let's get straight to the first question. So here we have an arrow diagram that shows the relation between set m and n. So the first part, state the image of 2. Image of 2 means 2 is my object, is mapped onto 1, so the image is just 1. Okay, the object of 4. Now you can see here, 4, object of 4 means 4 is the image. Yeah, image on the right hand side. So it has 3 objects, which are 6, 8, and 9. So we write here my objects are 6, 8, and 9. Okay. Next, does this relation represent a function? Give a reason. Yes, it does represent a function. Yeah. Why? Let me write here b. Because you can see every object has exactly one image. Okay. Uh, you can see 2 has one image, 6 has one image, 7 has one, 8 has one, 9 has one. Yeah. If you have multiple images, then it is not a function. Okay. All right. C. State the domain, codomain, and range. Okay. Domain is your first set. As you can see here, in your first set, we have 2, 6, 7, 8, and 9. Right? Yeah. Please use a set notation to represent the domain. Codomain represent everything in the second set. In this case, 1, 4, as well as 5. Right? And what is range? Range is the set of all images. That means everything on the right hand side here that has a corresponding object. So in this case, 1 and 4 is part of your range. Yep, because they have a corresponding object in your domain, whereas 5 is not part of your range because it doesn't have a corresponding object. Alright, simple. That's question number 1. Let's move on to question number 2. Arrow diagram on the right shows the function h. State the value of m. Okay, this one is a bit interesting because you need to think a little bit. Yeah, you can see -2 you map onto 3, 2 you map onto 3. So now when you see a -2 and 2 map onto the same object image, in our mind you'll be thinking that it must be a square. Why? Because any number squared is going to be positive, and you're going to get the same number, right? -2 squared is going to give us 4, 2 squared is going to give us 4, right? So we know that they will have the same image after you square it, right? So in your mind, you might want to try it out. -2 squared, we know is 4, okay? 2 squared, we know is 4. Okay, so but I'm not going to write 4 here. So I'm just going to write 2 squared and -2 squared here. Now you got to think, what should I add or subtract to get a 3? The answer is -1, right? If you put -2, you square it, you -1, you get 3. You have 2, you square it, you -1, you still get 3. Then let's test out with the rest. How about if you have 4, you square it, you -1. What would you get? You will get 15, which is the same here, right? So we can tell more or less what the function is all about, right? So to get m, we need to take 6 and you square it, you -1, right? 6 squared is 36, 36 minus 1, 35, right? So you can say m is just 35. Okay, now notice I didn't write the function notation first because I reserve it for part B. Part B, you have to use a function notation to express h in terms of x. In this case, we can say h dot x arrow x squared minus 1, right? This is the conventional, the standard way of writing, but you can also write hx equals x squared minus 1. All right, that is question number 2. Moving on to question number 3. Using a vertical line test, yeah, determine whether the graph on the right represents a function or not. If yes, is the function one-to-one? Test by using drawing a horizontal line. Now, a vertical line test means we draw a vertical line downwards and see uh, how many points it intersect the what do you call that, the y here. It, sorry, if the graph intercept the line intercept the graph at one point, that means you have one image. Remember, definition of function, every object must have one image. If it intersect at 2 points, for example, classic example like this, you have a graph like this, let's say, yeah, you cut this way, it intersect at 2 points. So this object X will have multiple images. So it's not a function. So when you draw vertical line downwards and it only crosses at one point, so we know an object here will have only one image. So is it a function? Yes. So you can say it's a function. Just write a function. Huh? All right. Then we test by using a horizontal line to test whether it's one-to-one, right? Remember, normally we test whether it has an inverse. A function has an inverse if it's one-to-one, right? So we draw a horizontal line this way. Now notice it cuts at 3 points. 1, 2, 3. That means you have 3x value that map onto the same y value, right? 3x value that map onto the same y value here. So we say this is a many-to-one relation. All right, so the question asks you whether it's a one-to-one. Answer is not a one-to-one relation. Not one-to-one relation, or not one-to-one function. Okay, next one, question number 4. Okay, this is a modulus function. Okay, let me start off by sketching the graph. Okay, to sketch a graph of modulus function, right? Let's say if you're a beginner, then I would suggest that you draw a table value y equals x minus 3. Okay, now this is before you modulus. So let's say we start off with x equals -1 and +7. Why must we draw these two? Because you can see the domain here. The domain means from where to where I must draw my graph. I must draw from -1 to 7. Okay, so let's put -1 inside. -1 minus 3, that will give us -4. All right, next one, 7 minus 3, it will give us 4. So if I just draw a basic modulus graph, then the graph will look, let me draw over here. Oh, I think, yeah, I think I draw like this. So this is -1 and 7 is further to the right. So you notice both of them, if I plot -4, it should be far below. Okay, I think my graph is a bit too, never mind, I'll just draw all the way down and see. Yeah, okay, my line is not very nice, sorry about that. So this graph should be -4 should be around here. Okay, so 4 is around here. Originally the -4 is here, 7 is over here, can you see? So you can just draw a line like this. Hold it. Okay, can you see? This is a straight line of y equals to x minus 3. Now, this is before you modulus. At the moment you modulus, what happens is that the part of the graph that fall below the x-axis will be reflected up. Okay, but can we just add two more points? I also want to add in x equals 0 and y equals to 0, because x0, y0 represent the x-intercept and the y-intercept. I don't have enough space, so I'm going to add in over here. So x, previously we put -1, you have 4, I put 4, I put 7, you will get 4 as well. I just add in 0. When x is 0, y is -3. When y is 0, x is actually 3. So you notice this will be -3 and 3. Okay, so but this is before you modulus. The moment you modulus this, right, what happened is that this part, the part of the graph that falls below the x-axis, is reflected up. So I'm going to draw this line here. Okay, and this line remains, can you see? And this one I will have to erase it, this one. You can change it dotted line if you want. Yeah, or you can just erase it. Okay, so once it's reflected up, it's gone. Right, now this is the graph of y equals modulus x minus 3. Okay, and the minus 3, when you reflect up, it becomes positive 3 over here. So there you go. That's the graph of y equals to modulus x minus 3, or the graph of fx. Okay, you're supposed to find a range. Okay, what I can, maybe I should write this as fx. So that is fx. Your range, we can write fx, we can write y. In this case, range represent the possible y value. Your possible y value is from 0 to 4. Any modulus graph, if you don't put a plus minus outside the modulus, the smallest is always 0. The largest is, in this case, is 4. So we say your range of f or fx here is between 0 to 4. Okay, first part with that. B. Find a range of values of x such that fx less than 2. Okay, we can use a graph, but before we use the graph, you can see here, 2 is probably here. I'll just show you by drawing a horizontal line. You notice that it would actually intersect here, y equals to 2 at 2 points. Our job is to find what are these two values, yeah, to find the range of values. So we'll start by letting fx be 2, and then modulus x minus 3 is now 2. Now remember, when you modulus something, a number, modulus means you're finding the positive value. So if I modulus negative 2, you will get positive 2. Yeah, we're finding the magnitude. The magnitude of minus 2 is just 2. If you modulus 2, you will still get 2. So when you modulus x minus 3, that x minus 3 has two possibilities. It's either a negative 2 or a positive 2. As you bring this over, x is now 1 or 5. So you can see this answer that we got here, it matches my diagram. Yeah, it's between 1 and 5. So what is the range of values of x? Well, this is my range of values of x. We say x is between 1 and 5. Yeah, we use the graph to figure out. All right, next one. On the same graph in part A, sketch the graph of y equals to x minus 3, hence obtain the values of x such that modulus of x minus 3 is now 2x minus 3. Okay, this is a bit more difficult. Well, the first thing is, how do you draw y equals to x minus 3? Well, normally I'll just let x be 0, y equals 0, right? X equals 0. Your y-intercept happens when x is 0, which is negative 3, all right? And then I let y be 0, my x is 3 over 2. Now you can use any other point. In fact, you can just pick maybe 5 or 7, any 2 points will do, right? As long as you can draw on your axis here. So I'm going to use a red pen. 0, 3 is probably here. 3 over 2, 0 is probably here. Just draw a straight line. All right. This is y equals 3x minus 2. Okay. Yeah, sorry, I'm missing the point. So now, how do you obtain the value of x for which your modulus x minus 3 is now 2x minus 3? Okay, so the first thing is, I'd like to point out to you again that when you modulus a graph, right, there are actually two parts to it. Okay, so the positive side of the graph is actually represented by x minus 3. So we say fx is actually x minus 3 for x more than equals 3. For this part of the graph here, on the right hand side, can you see I highlighted here, it is represented by the function y equals to 2x minus 3, right? If I sub x value or y value be the same. Sorry, x minus 3, not 2x minus 3, x minus 3. Okay, but for the negative side of the graph, which is over here, we actually get this graph after we flip it up, because originally it's below here, right? Originally it's down here. And how do you flip it up? Equation wise, we flip it up by putting a negative in front. When you put a negative in front, everything becomes positive. Now this is true for x less than 3. So for anything x less than 3, the modulus graph on the left hand side is represented by the negative of x minus 3. So the important thing is that we need to identify whether the straight line y equals to x minus 3 intercept the left hand side or the right hand side or both. Yeah, actually it depends on the gradient of the straight line. If the straight line y equals 3x minus 2 has a smaller gradient than x minus 3, it is bound to have two intersections. For example, it will probably intersect here when or when it has smaller gradient. In this case, the gradient is higher. Yeah, you can see the gradient is 3x. So it will cut higher at one point. It will cut only at one point, not two, right? So in this case, you can see it cut on the left-hand side, not the right-hand side. So the important thing is to put a negative in front for x minus 3 because it intersects with the left-hand side here, yeah, for x less than 3. So we just have to solve this equation. So multiply the negative inside. Okay. Since I don't have space, I'll move it up a bit. So this will be, bring it over, 6 equals 3x, right? And your x is just 6 divided 3, x is just 2. Okay, let's just double check, see whether it's true. And look at your graph here. I'm going to use a green pen. Can you see here, this point? It actually intersects at point between 1 and 2. So answer x equals 2 makes sense. Okay. Interesting question. All right, next question number 5. So arrow diagram on the right represents the part of the mapping of fx equals to hx plus k over x. So find the value of h and k. Okay, first we can say that fx equals hx plus k over x. Now look at your object 2 is mapped onto image 17. So we say f2 equals 17. Correct? Now in this case, when I sub in h2 plus k of 2, can I not write h2? We know it's h times 2 is just 2h plus k over 2 equals 17. Right? So what I need to do is to simplify this. Maybe I multiply by 2 to get rid of the fraction, because I know a lot of people don't like fraction. Yep, so I just multiply 2, get rid of it. Let's look at the second one. If I substitute 3 inside, I'll get 23. So we say f3 equals 23. So 3 times h plus k over 3 is now 23. Again, I don't like fraction. I multiply by 3. 9h plus k is now 69. Your favorite number. So what I need to do is to solve this simultaneously. So I like to use elimination. I can see that k and k, they have the same coefficient 1 here. So we're going to take equation 2 minus equation 1. 9h minus 4h is 5h. K minus k disappears. 69 minus 34 is 35. So h is just 35 divided by 5, which is 7. Alright, now as we sub inside equation number 1, you will get 4 times 7, h is 7, plus k equals 34, right? 4 times 7 is 28, 34 minus 28, k is just 6. Okay, first part, no problem. Second part, find the image of 6 under this mapping. Okay, first we know that h is now 7, k is now 6, right? So your function is fx equals to 7x plus x over 6. So the next thing I need to do is to sub in 6, right? Image of 6 means your object is 6, so 7 times 6 plus 6 over 6. 7 times 6 is 42, 6 over 6 is 1, you add together, answer is 43. Okay, right, next question, number 6. Okay, two functions f and g are defined by this. Fx equals to x plus 2, x minus 2, and gx is mx plus c. So given that g inverse 2 is f3, g f inverse 2 is 5. Find the value of m and c. Okay, so the first part is g inverse 2 is f3. Can we find what is f3? G inverse 2 is f3. f3, I'm going to put 3 inside. 3 plus 2, 3 minus 2. So G inverse 2 is now 5 divided by 1, which is 5. Now, for me, as if you watch my previous video, I don't like to inverse the function, right? Because I find it's a waste of time. I will just switch G5 is now 2. Yeah, if you don't understand this, let me say it again. 2 is here. When you inverse g, you end up at 5. If you start from 5, g5, you end up at 2. So basically, when you inverse and you switch to the original function, the object and image will now interchange. The image of 2 is 5 under the inverse function. The image of 5 is now 2 under the function g. So just switch the position. You don't have to inverse because we can just take this and sub inside your g. Your function gx is this mx plus c. So in this case, m times 5 is 5m plus c is now 2. Okay, so we can call this equation 1. So you notice I don't have to inverse. Yeah, it's much easier. All right. Okay, second one, g f inverse 2 is now 5. Okay, now in this case, no choice that we have to inverse because we need to find what is f inverse 2. Okay, so but for me, again, the way I do it is I let f inverse 2 equals y. Fy is now 2. What is your fx? Your fx is x plus 2 over x minus 2. Fy will be y plus 2, y minus 2. The result is 2. So we just solve for y. I'm not actually inversing the function, I'm just solving for f inverse 2. So y plus 2 is now 2y minus 4. Bring it over, bring over, your y is now 6. Okay, so my y is 6, then how? We will solve for g f inverse 2 because your y is f inverse 2, right? I'm going to put 6 inside, the result is 5. Yeah, your f inverse 2 is now 6, so g6 is now 5. Let's put 6 inside here. 6 times m plus c is now 5. This is my second equation. So just solve them simultaneously at equation 1, equation 2. Let's take equation 2 minus equation 1. 6m minus 5m, you get 1m. C minus c is 0. 5 minus 2, m is just 3. Okay, if you want to find c, just sub inside any equation, say equation 1. So 5 times 3 plus c is now 2, right? 15 bring over, 2 minus 15, c is negative 13. Okay, question number 7. So here we have a diagram that map function f, yeah, on that map set a onto b, yeah? So and b onto c. So we're gonna find in terms of x the function that map b onto a. Okay, so first of all, look at a onto b. A onto b means x onto 3x minus 2. So this function, let's look here, is fx, and fx basically is 3x minus 2. So when you want to map from b onto a, we're actually going backwards. So we are actually finding f inverse x. So we say let f inverse x be y, fy is now x, 3y minus 2 is now x, right? 3y is now x plus 2, y is now x plus 2 over 3, therefore f inverse x is x plus 2 over 3. Yeah, just to remind you, the way I do is a bit different from textbook. The textbook will always let fx equals y, then you solve for x, make x as a subject. I'm letting f inverse x equals y, so I'm finding y as a subject. Yeah, the reason why I use this is you can notice that in question number 6, it's easier. You don't have to inverse the function to find the value of a particular f inverse value. We can just straight away solve for it. Yeah, if you were to find the inverse function using that method, every time you need to find a particular inverse value, you need to find the inverse function first, right? Okay, so let's look at the second one, gx. Find gx. Okay, you can see here, this is 6x plus 1. 6x plus 1 originated from x. That means it's a function that we map from a to c. Yeah, and this function, we write this as gf. The reason gf, because f happens first, followed by g. F happens first, followed by g. We write gfx. Right. So you are given gfx. It's now 6x plus 1. So what you want to do is you want to find gx. Okay. Here, I would like to use the idea of f inverse x equals to x. I hope you still remember this, right? When you have, let's say, x, you inverse it. Let's say you get y, all right? So let's say I want to find out what is f inverse, right? My f inverse, let's say, is y. Then when you start from y, you will map back onto x. So f inverse is basically x. It's like you move backwards and you move forward, you end up at the same place where you started, right? So now, since I really know my f inverse, I know my f inverse from part A. So I'm going to put f inverse inside here. So when you put f inverse inside gf, my f inverse is x plus 2 over 3. Can you see that? Now the f and f inverse will cancel each other out. So now you're left with gx. And your gfx is already given here. So remember, composite function gfx means we put this bracket inside your gf. Gf bracket is 6 bracket plus 1. If you put a giant x plus 3 plus 2 over 3, this is x plus 2 over 3. We sub in the same thing. So this is x plus 2 over 3. Alright, now next, what do? We need to simplify this. Now, how to simplify? Oh, just cut these two, cut, left with 2, multiply inside. So your gx is now 2x plus 2 plus 1, which is 2x plus 3. Now, you can also choose to use the substitution method that we learned earlier in the earlier part of the chapter. Alright, but since we already have the inverse function, might as well we just use the inverse, right? It's much faster, right? Okay, part B. Find the value of x given that. Okay, I think I made a mistake here, sorry. This is now 4. Yeah, sorry, I wrote wrongly. This is 2 times 2 is 4. 4 plus 1 is 5. Gx is 2x plus 5. Okay, now part B. Find the value of x such that f gx is now 4x minus 3. Okay, I already know my gx. I know my fx, so we can put gx inside fx. My gx is 2x plus 5. I put inside my fx is 3 bracket minus 2. What do you put inside the bracket? 2x plus 5. So this is 6x plus 15 minus 2, which is 6x plus 13. And we know our fgx is now 4x minus 3. So I'm going to put 4x minus 3 here, right? Bring over. This will be 16 equals to x. Okay, negative 16 equals to x. X is just negative. Okay, that's number 7. Okay, moving on to number 8. Right. Okay, so here, the first part, I think you want to find the value of k. Remember, a function becomes undefined when your denominator is 0. You can't take, like, for example, 3 divided 0 is undefined. It's basically like the graph of y equals 1 over x. Your x, when it approaches 0, your y value approaches positive infinity or negative infinity, so we say it is undefined. Okay, so your function becomes undefined when x minus 1 is 0, x is 1. So it is given here, x cannot be k. So that means your k must be 1, right? Okay. Next, find the value of m and n. So here we have to form two equations and solve them simultaneously. We start off with f2 equals to 3. So if I put 2 inside my x, this is n, sorry. This is n. The result is 3. So let me rub this off. This is going to be m plus n equals 3. Let's call this equation 1. And if you put, let's say, 3 inside, you get 2 from here. This will be m over 3 minus 1 plus n equals to 2. So this would be 2, right? So maybe I'll just multiply by 2. This is 2, so I just times 2 straight away. M plus 2n is now 4. Equation number 2. Reason why I times it over, because it's easier. I don't like fractions, so it's easier to solve it this way. Let's take equation 2 minus equation 1. n minus m disappear, 2n minus 1n is just n, 4 minus 3 is just 1. So n is 1. As we sub inside equation 1, m plus n is now 3, n is now 2. Okay, that is part B. Right, I got m equals to 2, n equals 1. Okay, next one, part C, f2x. Okay, what is f2x? f2x simply means f of x is what we call a iterated function or repeated function. A function repeats itself, so you put fx inside fx. Okay, we know our fx now. Fine, fx is m. In this case, m is 2 over x minus 1 plus n. My n is 1. So I'm putting this inside fx once again. Okay, so here's the thing. You need to remember fx is 2 over x minus 1 plus 1. So if you put this thing again plus 1, sorry, a bit hard to see. Okay, maybe I write a little bit bigger. Write a little bit bigger. Your fx is 2 over x minus 1 plus 1. So if you put 2 over x minus 1 plus 1, you need to put 2 over x minus 1 plus 1. Can you see that? So this is now 2, let me write a big 2 here, a big 2 over 2 over x minus 1 plus 1. There is another minus 1 here, plus 1 here. So notice the minus and plus and minus cancel each other out. Alright, so let's move this up a little bit. So this will be 2 over 2 over x minus 1 plus 1. Right, so if you invert this, what would you get? So let me just flip it upside down. So this f2x is now 2 times x minus 1 over 2 plus 1, which you can cancel 2 and 2, left with x minus 1 plus 1, which is just x. Yeah, very interesting, right? Alright, lastly, we are finding f inverse 2, part D. Okay, so we let f inverse 2 becomes y, fy is now x. Okay, remember your fx is 2 over x minus 1 plus 1, so this will be 2 over y minus 1 plus 1 equals to, okay, I wrote this wrongly, fy equals to 2, this is 2. Alright, we interchange it. Yeah, remember just now I talk about the how to interchange the object and image. So you're going to bring the 1 over, 2 over y minus 1 is now 1, y minus 1 is now 2, y is now 3. Therefore your f inverse 2 is just 3. Okay, that is question number 8. Let's move on to number 9. Okay, diagram shows the function y equals x cubed minus 3x squared minus 1 plus 1 for the domain of x between minus 3 and 1. So state whether the function is discrete and continuous. You know what's the difference between discrete and continuous? Discrete are just single value like this. You've seen this before, right? Like that, or it can be on the straight line like this. A continuous, it can be a curve, can be a straight line, but the x value will take a range of values. A discrete will take a single value. For example, this one will be 1, 2, 3, 4. So your domain will look like this: 1, 2, 3, 4. These are discrete. Continuous, maybe your domain is between minus 1 and 4, so we say x between minus 1 and 4. This is continuous. Continuous, your domain and range are in the form of a range, right? Whereas your discrete is, they are all single value, right? Countable value. Okay, so let's look at the solution. The answer for the first one we say is continuous, right? If they ask you why, you say the domain is in a range. The domain is in a range, is continuous. Okay, the range of values of f correspond to the domain here. Okay, your range is your possible y value. You can see the smallest y value I have is minus 4. The largest y value I have is 4. So we say that your fx is between minus 4 and 4. Okay, B. By applying the horizontal line test, determine whether f has an inverse function or not. Okay, horizontal line test, we just draw this way. You can see that it actually intercepts at 3 points. Yeah, that means a many to one relation, and multiple x map onto a single y, right? When it cuts only at 1 point, that means it must be 1 to 1. A 1 to 1, it would have an inverse. In this case, it has no inverse. That's it. Okay. All right, moving on. Let's look at question number 10. Okay, given that function fx equals to modulus x and fx is also x power 4, they are not one-to-one. So determine whether the suitable condition for the domain of f such that new function becomes one-to-one. Okay, so if you want it, I can sketch for you. The graph of modulus x is a V-shaped graph like this. Okay, like that. Okay, so it's definitely not one-to-one. Why? Because you have multiple x that map onto a single y. Right? Multiple x map onto a single y. So if it's not one-to-one, then it has no inverse, right? So how do you make it one-to-one? Okay, we call this a domain restriction. Domain restriction means we don't normally we say, okay, now from at maths form 4 we don't say this, but for IGCSE A levels we write this up. X is an element of real number. That means x can be true for all x. You can take all any value of x. We say x is an element of real number. This is your domain. But if you restrict the domain, you say, okay, I don't want the left hand side. I just change this to x greater equals 0. That means the function, okay, sorry for the ugliness, so it's supposed to be only one part on the right. Yes. So this is now a one-to-one. So by restricting the domain, by trimming off the left-hand side, that means this function is valid for domain of x greater equals 0, then it will become one-to-one. Now same goes to y fx equals x power 4. Now x power 4, the graph is somewhat similar to quadratic, but it curves very slowly here. It goes up very fast after x more than 1. So it actually looks like this. Okay, sorry, again, a bit ugly. It must like be symmetrical joining this way. Okay, now again, it's a many to one relation, it's not one to one, so trim it off to make it one to one. Again, same thing, we take x greater equals 0, so we trim this part off. All right, and so the question is, uh, determine the suitable condition in the domain such that this two becomes one-to-one. Answer, we can just write once only, yeah, because it's the same. You don't really need to show the graph, but I just drew the graph for you for your understanding. All right, so your condition for your domain is x greater equals 0. Okay, from A, find the inverse for each function. Okay, let's start. For the first function, right, because we know that fx, if you define modulus function, we can say it's true for x. Your modulus function, the modulus of x, sorry, is x for x greater equals to 0, and it's negative x for x less than 0. Since we already trim our domain to just x greater equals 0, so we will be using this fx equals x. So your b, you are actually looking for fx equals x. Okay, here is the interesting part. What happens if you inverse your fx? Don't need to count. It is still the same. Your f inverse x is still the same. Yeah. Why? When the function map onto itself, the inverse, the x, you inverse it, it is the same as the function itself, right? So in this case, it's still the same as x. Okay, so no calculation required. You can just write this. Okay, how about x power 4? For x power 4, right, I think we don't need to show working. We know inverse means opposite. Like for example, fx equals to x plus 3. What's your inverse? The opposite operation is x minus 3. If I give you fx equals to 2x, what's your inverse? Your inverse is x over 2, right? If I give you fx equals to x power 2, what's your inverse? Your inverse is just square root of x. It's just the opposite operation, right? So what is the opposite operation for x power 4? Well, you can call this a quad root. So the f inverse x, you can either write as x power 1 over 4, or you can say quad root of x. Okay, so no need to write the working because it's actually the same thing. Right. Okay, number 11. This is very interesting. If a graph function and its inverse function intersect, would the two graphs intersect on the line y equals to x? Okay, now textbook's answer is not very clear. I just want to highlight for you. When you have a graph, a typical graph, let's say, y equals to fx. Let's say your fx, I'll write fx equals to x squared, the moment you inverse it, the opposite. Okay, my graph, I need to curve a bit more so you can see the difference. So let me redraw this. I need to curve it a bit more. Uh, one more time. The graph is supposed to look like this. Okay, the moment you inverse it, the graph will look the other way around. Okay, let me use a different color. Let me just draw the inverse this way. The opposite of x squared is square root of x. Now both them actually, they do intersect, as you learned earlier probably, they do intersect each other in the line y equals x. Now y equals x is your axis of reflection. Okay, a reason being is here, for example, when you map, let's say, uh, for example, f2 you map onto 3. Your f inverse 3 is now 2. Can you see? You interchange object image. But what if I have f2, let's say I map into 2. My f inverse 2 will still be 2. So in the first case, your coordinate is 2, 3, right? The inverse will be 3, 2 when you switch position. In this case, your coordinate is 2, 2. The inverse is also 2, 2. So that means that if your fx is the same as your f inverse, right? Now this is only true if your x and y values are the same. If your x and y values are the same, they must both lie on the line y equals x. Okay, so the answer is supposed to be yes. Okay, but the next question is, what is the possibility of two graphs intersect on other lines? Okay, the answer is there is a possibility, right? I can give you a few examples. The main thing is that if the function is the same as the inverse, they will intersect at the infinite number of lines. For example, classic example, uh, for reciprocal function, a basic reciprocal, it can be 1 over x, 2 over x, 3 over x, 4 over x. You can test it out. Okay, I'll just show you. This is for the explanation part. So we say f inverse x becomes y. Fy equals to x. So 4 over y is now x. You bring up, bring down, y is also 4 over x. So my inverse is the same as the function itself. So we look at this and wonder, what happened? Oh my god, the function and the inverse is the same. How? Did I make any mistake? No, nothing wrong. It's just that so happens this function, when you inverse it, the function is the same. The inverse is the same as the original function. Now, if you were to sketch this graph, it looks like this. A curve like this, right? For example, you may want to put, okay, y equals 4x, you put 1 here, let's say, it will map onto 4. Now, when you inverse, it's supposed to be a reflection in the line y equals to x. When you inverse, it becomes 4, 1, right? You flip over, it's 4, 1. Now, you may have another line y equals to, another point y equals 2. You put 2 inside, 4 over 2 is still 2, 2, 2, right? Now, imagine drawing this and this, the f and the inverse on the same axis. So we'll draw inverse here, what happened? See? They will overlap, right? They will overlap. So is there a possibility that they intersect each other at other line? Yeah, they intersect each other infinite possible, possibly possible points. There a lot of other points. All right. Now, not only this function, I can give another example. You can say, for example, 3 minus x or k minus x. Yeah, it can be 2 minus x, 5 minus x, 10 minus x. You go and inverse this function. It is the same. The inverse is the same as the original function. Another example will be the square root of 1 minus x squared, right? You go and inverse this, what do you get? You get the same thing, right? So this graph will actually overlap each other. Like, for example, the 3 minus x graph is like this. Yeah, when you take the graph, you reflect on the line y equals x. The function and the inverse will actually overlap. When you draw this, this is like a circle. When you inverse it, the graph and the inverse will actually overlap on the same graph, right? So they will intersect at more points, right? So how do you answer this? Okay, what is the possibility that two graphs intersect each other? We say that uh, it is possible. I'll say it is possible. It is possible for the two graphs to intersect add other lines. Yeah, other lines. For example, when the function is the same as is inverse, the graph of y equals fx and y equals f inverse will overlap. Okay, so they will actually intersect at more points. Okay, all right, let's look at number 12. Given gx equals ax plus b over cx plus d, find f inverse. Okay, this is a very interesting question as well. I like this question actually, right? Using the formula f inverse, determine f inverse for each of the following. So number, number one, we know that f inverse, to inverse this function, I'm going to write f inverse x equals to y, fy is now x, ay plus b over cy plus d is now x, ay plus b is cxy plus dx. So bring all the y on the same side. I'll bring this over, bring this over. So ay minus cxy is now dx minus b. Factorize your y, a minus cx equals dx minus b. So my y is dx minus b, x minus cx. Oh, you can't see. Let's move this up a little bit. Okay, so my y is fx is therefore dx minus b. We can write minus cx. Okay, I think I wrote this wrongly. My a looks ugly. This is a. This is a. This, um, I'll write c in front and a at the back, just to show you what actually happens from here to here. Now you notice what happened when you, this is inverse, sorry, I need to write this clearly, f inverse. Okay, what happened when you inverse this? We are actually inversing a general reciprocal type of function, and you can see that when you inverse this, right, okay, two things happen. Number one, your A and D interchange position. Look at this is your A and D, right? Look at A and D. Sorry, I need to highlight this. Then I'll erase it. Look at A and D. Oops, interchange position. Right. Number two, uh, we put a negative in front of B and C. Look at this, your B and C. Look at your original B and C. You see that? So your A and D interchange position, your B and C, you put a negative in front. So if you when you're from 5, you learn maths matrices, you learn about this inverse. We actually interchange position of A and D and put a negative in front of B and C. We do that in your mock maths from 5. Okay, so now this is your final answer, the f inverse. Now you can write x naught equals to, you let minus cx plus a equals 0. Cx is a, cx is a over c. So we will see. All right, now use this formula. We want to find the f inverse. So it's like a shortcut, fast and furious way. Okay, let's see how to inverse Roman 1. So you put interchange a and d. My a is 1. You can see here my a is 1, my b is 8, my c is 1, my d is negative 5. So we put negative 5x, b is 8, put a negative in front, c is 1, put a negative in front, d I switch down, D I put up, A I put down, plus 1. Okay, but normally we don't want to have multiple negative. If you see an equation with multiple negative like this, right? So we just basically multiply top and bottom with negative 1 to simplify further. I times with negative 1, I times with negative 1. So this will be 5x plus 8x minus 1, and we say x not equals to 1. Okay, Roman 2. Your fx is given here. Okay, my a is 2, b is minus 3, c is 1, d is 4. So we interchange a and b again. All right, I put 4x, this is plus 2. Okay, I put a negative in front of b and c, so my b is negative 3. You put a negative in front, it becomes positive 3. C is 1, put a negative in front, is minus 1x. Uh, Now, normally we don't write like this, it's a bit ugly looking. So what we do is we just put 2 minus x. Yeah, put the x at the back, x not equals to 2. Okay, now next, part B. If C is non-zero, what are the conditions such that f is the same as f inverse? Okay, this is very interesting as well. Okay, right, very interesting. So when your fx is equals to f inverse, so we can write the general formula ax plus b, cx plus d equals to f inverse. My f inverse will be 4x, sorry, not 4x, we write the general formula, which is bx minus b minus cx plus a. Okay, now I purposely write minus cx plus a because I need you guys to compare, right? So we need to multiply this left hand side with minus 1 and minus 1, right? So that I can see ax plus b over cx plus d is now minus dx plus b and cx minus a. So the reason why I do that is because I want to make this b the same. See the b here? The b here the same, right? And at the same time, you can compare your c. Your c the same now, right? All right, the same, right? So what is the condition? Now look at your a and b. Now let's focus on your a, o, e, and focus on, okay, should I use yellow? B and B. So what is the condition? In order for these two to be equal, the B values are the same already, right? So in order for them to be equal, your A must actually be negative D. Or you can say your D must be the same as negative A. You compare the red one, the coefficient X on your numerator, A is now negative D. And you compare the constant in your denominator, your D is now negative A. So you just write one of them will do, right? A is negative D or D equals to negative A. So there you go. That's the condition for which fx is the same as its inverse. All right, let's move on to number 13. Number 15. Sorry, 13. Okay, this one they say one-to-one function is defined by fx equals x squared minus 2x for x between 1 and 3 using GeoGebra software draw the graph. Okay, so here I can't use GeoGebra software, so I'm just going to draw using hand, but I would plot the point one by one, so it's easier for you to see. Okay, so the first point we're going to plot is since they say between 1 and 3, yeah, so actually you will learn this in your mock maths chapter 1, how to draw x squared minus 2x graph, but since I assume that you haven't learned yet, so I'm just going to use 3 points, x and y, 1, 2, and 3. Just use 3 points, 1, 2, 3, 1. When you sub 1 inside, 1 square minus 2 times 1 is also 1. If I sub 2 inside, 2 square minus 2 times 2 is 0. If I sub 3 inside, 3 square is 9. 9 minus 2 times 3, 6. I still get 3. Okay, so I have 3 points here. And I'm going to draw the graph. And should I draw here? I draw here. So, I need more space. So let's draw over here, x and y. Okay, so the first point is 1. I put minus 1, 1, 3. Yeah, this is minus 1, 1, 2, 3. This is minus 1, 1, 2, 3. Okay, so first one is 1 minus 1 over here, 2 0 is over here. Yeah, my 2 should be nearer here. And the third point is 3 3 over here. You can see that 3 points. We just draw a curve. It's a quarter figure, so we know the graph looks like this. Okay. Alright, my 2 looks a bit ugly, so just fix this a bit. Okay, now next, if you can plot the point, the point is 1 minus 1, this is 2 0, and this is 3 3. Okay, now this is 1 2. Okay, next they say state the range. Okay, what is the range for Roman 1? Your range you can see from the graph, the smallest value is minus 1, largest value is 3. So your range of fx is between minus 1 and 3. Okay, Roman 2, now we are going to draw the graph of f inverse. and state the domain. Okay, now since you really know that when you inverse a function, the object and image will interchange, your x and y will interchange, right? Yeah. So for example, if I put f1, I get -1. When you do f inverse, -1, you will get 1, right? We just interchange them. So I'm just going to plot this inverse using blue pen here. Where's 1, -1? 1, -1 is over here. Second one, 2, 0 becomes 0, 2. Third one, 3, 3, you interchange is still 3, 3. So it goes like this. Okay, better. My 2 is a little bit off, but it's okay. All right. Now, I've drawn the graph now, the graph of f inverse, right? And state the domain. Now you can see domain are your x value. You can see your x value here. Maybe I plot the point for you, right? So this is -1, 1, 0, 2. Okay, 3, 3 I don't have right because it's the same point. So your possible x value is between -1 and 3. So your domain for f inverse is -1, 3. Okay? Alright. Now then, what can you say about the range of f and the domain of f inverse? Right? Okay, so I write, what can you say? We can say that the range of fx or f is the same as the domain of f inverse. Yeah. So when you reflect the x and y interchange, the domain of f inverse is the same as the range of fx. Okay, next part B, Roman 1. Okay, this is B, but this is B Roman 1. Okay, is the graph of f inverse the reflection in the line y equals x? So first we have to draw the line y equals x. Okay, where's y equals x? Okay, I'm going to draw, this time I'm going to use red line, y equals to x. Normally we use dotted line, but you can use a solid line as well, right? Okay, now just use solid line here. Okay, is it look good? Okay, now I think I should just delete the dotted line. Yeah, it's better to delete the dotted line. So I use, okay, it looks a bit off. One more time. Okay, still a bit off when I straighten it, right? My line is not so straight. Okay, one more time. Okay, let's just, okay, just let it be, right? Okay, y equals x. Okay, it looks like this. Okay, so we can see from here that the graph of the line y equals x is a line of reflection. So we say, is the question, B Roman 1 is that, is the graph of f inverse the reflection of graph f in that line? Answer is yes. Alright, Roman 2. Is the point 0, 2 on the graph f inverse the reflection of the point 2, 0 on the graph of f in the line equals x? Again is a yes. What conclusion can we make? Okay, well, we can write any point, now I probably don't use xy because we already use xy here, so I just follow answer the textbook. A textbook use AB at any point AB, like for example this is AB, right? When you reflect over, this will be BA. You can use any other symbol, so any point of BA, any coordinates on the graph of f inverse, right, is a reflection of the point, or should I say of point AB. Okay, you can't see it. AB, I put AB down here on the graph of f in the line y equals x. So y equals x is your line of reflection. Okay, so we're done with number 13. Let's move on to number 14. Okay, so the price P in RM of an item and the quantity X sold the demand, follow the demand equation, Px equals 100 minus 1 over 4x. Whereas cost C to produce is given by this C equals square root x 25 plus 600. Assuming all items are, or the products are sold, so calculate cost of C as a function of price B. So cost. Now, if you want to find cost as a function of P, so that means I must give you x. To give you x, you must go back to this formula, price in terms of x, and make x as a subject. So we bring over. So 1 over 4x equals to 100 minus p. X is 4 times 100 minus p. So you can call this equation 1. Up to you. You just sub inside your c. I think you don't have to write that, right? So your c, can you see the x there? So you put a square root. Your x is 4, 100 minus p. Now, I don't want to multiply the 4 inside, simply because I can square root 4. Yeah? If you times inside, then you have to factorize back. So you divide by 25 plus 600. So square root 4 is just 2. Keep the 100 inside. Don't need to do anything over that. Over 25 plus 600. So, right, cost is a function of p. Okay, next. Calculate the cost of producing the item if 1 unit or of the item sold is 36. Okay, 36. I think they should say 1 unit. Okay lah, one price of 1 unit, yeah, is 36. So we're going to put 36 inside. 2 square root 100 minus 36 over 5 plus 600. Okay, 36 minus 100 minus 36 is 64. Square root 64 is 8. Divide by 5 plus 600. So this is 16 divided by 5. 0.64 plus 600. So it's 600. If you put in ringgit, RM, right? Yeah. RM, so it's RM 600.64. Okay, that is number 14. Okay, one more. Okay, last one, I think this is the pivot in second of a simple pendulum of is a function of length L defined by TL equals 2 pi over square root L over 100 over G. G is 10, gravitational acceleration. So they say use GeoGebra software. I don't have GeoGebra software to share with you here. So I'm just going to draw the graph like this. Okay, horizontal like that. You can see, yeah? Maybe not too high. Not too low. Okay, not too low. Like this. Okay, I think this is L, this is T. Okay, so now, by the way, just to, this is extra knowledge. We know y equals to x squared, the graph looks like this, right? So x, if I use x equals to y squared, the graph actually goes this way. And if you square root it, by right you should put a plus minus, right? The plus positive side is the one on top. The negative side is the one below, right? So if you want to draw this graph, can you see? A pi is just a constant, so it doesn't affect anything. It affects the curvature of the graph, how curvy the graph, but it doesn't affect the position of the graph. So the graph would actually have a shape like this. The positive square root, you can see the 2 pi in front is positive, so we just draw a graph like this. Okay, pass through 0. I'm just going to rub this off, yeah, and I'm going to label this as T. This is TL equals 2 pi square root. Now they say use G as 10, so I just write L over 10. Okay, next. Second one, you're going to draw TL equals 2 pi square root L plus 4. So now the thing is, this is what we call a transformation of graph, right? So basically, when you plus 4 to your variable, you're actually shifting the graph to the left by 4. Right? You're shifting the graph to the left by 4. For example, classic example, a y equals x squared, the graph looks like this. The moment you put a plus 4 squared, you're shifting the graph to the left by 4. Now, it is true for types of graph, yeah? When you plus minus to your x, the horizontal variable, it just shifts to the left, right? In this case, plus, shift to left by 4. So I'm going to draw the same graph here. So it goes, whoa, same curvature, but this is minus 4. Now, if you want to find your y-intercept, you can find your y-intercept if you want, but by substituting L equals to 0. So if you put 0 inside, okay, so let me put this away. this will be um, 2 pi square root 4 over 10. If you use your calculator, I think you key your calculator, you should get about 3.97. So approximately 4, approximately 4, 3.97, up to you. Maybe I just use 3.97. Yeah, 3.97 around there. Okay, now you don't really have to plot this, you can, because you can use a GeoGebra software. Okay, this is TL equals to 2 pi square root L plus 4 over 10. Okay, the next one you notice instead of adding 4, we multiply 4. It's like y equals x squared, the graph looks like this. The moment you have a 2 in front or 4 in front, yeah, you're actually stretching it up, right? Before this, where x is 1, y is 1. Now x is 1, y is now 2. So you pull it upwards. We call it a vertical stretch. So from the original graph here, we stretch it up, so it goes like this, a lot higher, right? So this is the graph of TL equals to, oh, got no space, 2 pi square root 4L over 10. Sorry, no space. Yeah, squeeze in there. All right. Do we have to find a point intersection? It still starts from point 4. Okay. So that's the tree graph. You can test it out using a software, graphing calculator. I personally like Desmos graphing calculator. Yeah, you can find online and just draw it out. Okay. Next one. How does the change in length affects the period t of the pendulum? So now, of course, you can see when you increase the length, like for example L plus 4, your t value increases. Yeah, your t actually higher, your oscillation period higher, right? Can you see? The t plus 4 is this graph here. It actually increases, and if you multiply by 4, it also increases from the original graph, right? So how do you write your answer? We say now, um, we can say that the period t depends on the length of pendulum L. As the length increases, the period or the oscillation period also increases. All right. Okay, so that's the end of our discussion. Yeah, I hope you enjoyed this video, right? And learned something from it. We have a lot of series of books, notes and tutorial, past topical practice, past year question, drill practice. Yeah, if you're interested to get more material, working material, or to join our class, right? My class. Yep, you can let us know, right? By contacting us. Thank you for watching this video. I'll see you in the next one.